So in this video, we're going to talk about the concept of implicit differentiation and why, why is that thing? Why would we care to do that? So let's say we had a parabola like y equals x squared, something like that. And there might be a reason the scale's off, but we'll pretend I'm doing a good job drawing this. Hopefully it'll be nice and pretend along with me. We have some tangent line, right? We can find the slope of that parabola at the point 1 comma 1. Again, the scale's off. Let's not worry about that. So if I want, I can say, oh, well, y prime equals 2x. And I can go, okay, well, when x equals 1, y prime, well, that's going to be 2 times 1, which is 2, right? The slope is 2 there, right? I can also say that dy dx equals 2x. I can use the Leibniz fractional notation, and I can say that dy dx with a vertical line with a little 1, or if I want x equals 1, well, that's going to be 2, right? For the same reason. These values are both 2 for the same reason. So this is an approach we've already used. It's primarily a notational difference. It's just a way to say that we're finding the derivative. What's the slope at that point? Another thing that I can do is I can take the equation y equals x squared, and I can apply the derivative with respect to x to both sides. And this is something that we have not done before. And it might not be clear yet why we would do that, but I can then say, okay, what is the derivative with respect to x of y? Well, the notation dy dx is what that represents. Dy dx is that derivative. And then, of course, the derivative with respect to x of x squared using the power rule is 2x. So this step here of saying that we're applying the derivative to both sides is something very new. We have not done that before. But in principle, it kind of has been what we've been doing this whole time. We just never said it this way, and we never wrote it this way, but it really is what we were doing. This allows us to broaden what we're applying it to. And what do I mean by that? Well, let's take a different equation. Instead of y equals x squared, let's take this. Let's say I don't have a parabola, but I have a circle, right? Let's say I have a circle. We're going to try to use these auto draw tools to full effect. Call it good enough. Let's say this is a circle of radius 5, right? So this point up here, this ordered pair is 0, 5, and this ordered pair here is 5, 0, right? So you might remember from algebra that there is an equation that describes, or a format for an equation that describes what a circle is. X squared plus y squared equals r squared. This describes a circle, right? Basically, a circle is the set of all points that are equidistant from some central point. So in this case, the origin. These points on the circle's edge are all 5 units away from the center being at the origin, right? So I can say that x squared plus y squared equals, with the radius is 5, 5 squared is 25. This is the equation that describes the circle. Now if I said, well, you know what I really want is I want the point at 3, 4, I want that tangent line. I want the line, or rather, I want to calculate the slope of the line that is tangent there, which we can do. Now, one way to do that we're going to find is maybe overly complicated is I can solve for y. I can subtract x squared on both sides of this equation, and I can apply the square root function and get y equals plus or minus the square root of 25 minus x squared, and I can go from there. Now the problem with this is this plus minus. This means we don't have a function, and so calculus does not play very nice when we don't have a function. So I could say, well, let me pick the plus, because I know that I'm working with the top of the circle, the top half. So I could say, you know what, let's just use the plus. Let's say I'm going with, I choose y greater than 0, so we'll say that y, y equals 25 minus x squared to the 1/2 power. And we could go find the derivative with that, and it would work fine. No big deal. But this is getting increasingly complicated. I have to solve for y, and I have to choose top half versus bottom half. I'm going to stop this approach here because it just gets increasingly complicated, especially now we have to use the chain rule, and I'm going to have to use the power rule and the chain rule and the power rule again. It's going to get really messy. I want to backtrack a little bit and go back to this equation and try this other approach of applying the derivative to both sides. This is what's called implicit differentiation. Backtracking a little bit more, the way this equation is written, this is called an explicit equation. You're given y equals some formula, right? This is called an implicit equation. You are not given y equals some formula with x, but it's kind of implied, yeah, there's a graph in there somewhere, but you're not told y equals f of x. You're given a function, right? It's handled differently. But we can still use this approach here of applying the derivative to both hand sides with this equation. We do not have to get y by itself. We can if we want, but as I point out, this is starting to get a little bit cumbersome. Let's not do it that way. So I'm going to just take this equation and apply the derivative to both sides. So I've got x squared plus y squared equals 25. Am I running out of room? No, I got space. Okay. Now I'm going to apply the derivative to both sides. Now the right-hand side is going to be pretty easy because we just have the derivative of a number. As you probably know right away, the derivative of a number is 0. So that's easy. On the left, I'm going to use the sum rule, which we haven't used directly in a while. We mostly use it without saying what we're doing. We just go ahead and utilize it and gloss over the details. But I'm going to write it out this time because I want to be very careful to not skip anything important. Equals 0. So when we go to find this derivative, the derivative with respect to x of x squared, it's the power rule. We've been doing this for over almost 2 months, around 2 months. This maybe is easy by now. It's over 2 months. So this is just 2x. Just apply the power rule. Done. Easy, right? Now here, the difficulty is that we have two variables at work. The variable with which we are taking, with respect to which we are taking the derivative is not the variable that we have in the expression. Y is implied to be some function of x. Basically, y equals some g of x. What is it? I don't know, but it's some function, right? So when we find the derivative of y squared, we have to use the chain rule. When we have y squared, the squaring part, this is the outside function. And the y, this is the inside function, okay? So, maybe this is going to be clear enough. I hope so, perhaps not. I can always make a video going into more detail. I'm going to skip a little bit of detail because maybe I've given enough context, and you're kind of already expecting what's going to happen. I'm hoping, at least. So when I apply the chain rule, I need to temporarily ignore the variable at work and just find, well, what's the power rule? The power rule is the outside function right now, right? So that'd be 2 times whatever. That's the power rule. 2 times something. But then times the derivative of the inside. Well, what's the inside function again? Y is the inside function, right? So y both sits inside the parentheses and nothing happens to it because of the chain rule, right? But then also we have to multiply it by the derivative of the inside function. So d dx of y. Okay, so we apply I'm going to erase this, but I want to make it clear. Apply the power rule, and then we apply the chain rule. Okay, to get those two factors. So if you're clear on the chain rule, and the chain rule makes sense to you, maybe this is pretty transparent and easy to follow. If you're not so clear on the chain rule, this might be really confusing. So please email me, ask for using Zoom or WebEx or something, we can talk more about these details. Maybe I can make another video going into more detail, but this video is getting long enough. I don't want to drill down into every point of detail. So maybe that's enough. And of course, we'll have other videos where I do more examples. Maybe by seeing those, this will be enough detail. So, going forward, this equals 0, of course. So we've got 2x plus 2y times dy dx equals 0. So the hard part is over. The hard part is done. I just need to now get dy dx by itself. So phase 1 of implicit differentiation is apply the derivative to both sides, use the chain rules needed, power rule, product rule, what have you, whatever it is that you need. And once you apply those, now you have an equation where you have three things. You got x, you got y, you've got dy dx, which is what you really wanted to find to begin with. Now we're basically solving an equation. The rest is algebra. So although this looks complicated, really what we have is like, hold on, excuse me. We have like 8 plus 10 times a equals 0, and we're solving for a. Subtract 8, divide by 10. That's it. It's really not difficult at this point. It's easier than it looks at this point. So I'm going to subtract 2x on both sides. So 2y times dy dx equals, sorry, hold on, fix that x, equals negative 2x, and then I can divide by 2y on both sides. So dy dx equals negative 2x over 2y, and of course that reduces to negative x over y. So there's our derivative, negative x over y. And if we backtrack a little bit, if you had continued this route, you would get an equivalent answer. It would look different, but it would be really the same thing. And again, if you want more detail on that, email me or put in the comments. I can make another video going into more detail if necessary. Anyway, I wanted the slope at the order pair 3, 4. Right? So, dy dx at the ordered pair 3, 4, this vertical line means we're going to evaluate, and then 3, 4 means put in 3 for x, put in 4 for y. This is notation you'll probably see in the homework and perhaps on exams. I don't remember the notation that the exam is going to use offhand. Well, use this formula. 3 in for x, 4 in for y. So negative 3 over 4. So negative 3/4, that is the slope of this tangent line. Okay? So by using implicit differentiation, we can find tangent lines on graphs that aren't functions. This graph fails the vertical line test, right? If you try the vertical line test, it fails. It's not a function. But you can use implicit differentiation, treat y as an implied function of x, and get a slope anyway through this process of applying the derivative to both sides. So that's both the concept, our first most basic example. Next video we'll have another example of this, and we'll have a few more after that.